In this video, we're going to be continuing to talk about confidence intervals, specifically confidence intervals for a population mean. Now, the confidence intervals for mu when sigma is known. So the general formula for a confidence interval for a population mean mu when our x bar is the sample mean from a random sample, the sample size n is large, meaning that n is greater than or equal to 30, and our sigma, our standard deviation, so the population standard deviation, is known. Now, these are the properties of the sampling distributions of x bar. That equation, or that formula rather, is x bar equals plus or minus our z critical value times the sigma divided by the square root of n. X bar is our point estimate. Sigma divided by the square root of n is our standard deviation of the statistic. And this is our bound on error of estimation. But is our sigma typically known? Not really. This confidence interval is appropriate even when n is small, as long as it is reasonable to think that the population distribution is normal in shape. Let's look at an example. Cosmic radiation levels rise with increasing altitude, promoting researchers to consider how pilots and flight crews might be affected by increased exposure to cosmic radiation. A study reported a mean annual cosmic radiation dose of 219 mREMs for a sample of flight personnel of Xinjiang Airlines. Suppose this mean is based on a random sample of 100 flight crew members. So we're going to let sigma equal 35 mREMs. So we're going to calculate and interpret a 95% confidence interval for the actual mean of annual cosmic radiation exposure for Xinjiang flight crew members. So first we need to verify that the conditions are met. Our data is from a random sample of crew members. Our sample size n is large. We have 100. That is definitely greater than or equal to 30. And our standard deviation is known. So we can go ahead and plug that in to our formula. Our z critical value for a 95% confidence interval is 1.96, and that's going to give us a lower bound of 212.14 and an upper bound of 225.86. But what does this mean in context? What it means is that we are 95% confident that the actual mean of annual cosmic radiation exposure for Xinjiang flight crew members is between 212.14 mREMs and 225.86 mREMs. Now, what would happen to the width of this interval if the confidence level was 90% instead of 95%? Yeah, it would decrease. So what about the confidence intervals for when our mean when our standard deviation is unknown? So when sigma is unknown, we use the sample standard deviation S to estimate sigma. In place of z-scores, we must use the following to standardize the values. T equals x bar minus mu divided by S divided by the square root of n. The use of the value of S introduces extra variability. Therefore, the distribution of t values has more variability than a standard normal curve. So there's some important properties of t distributions. T distributions are described by degrees of freedom, or dF. One important property is that the t distribution corresponding to any particular number of degrees of freedom is bell-shaped and centered at 0, just like the standard normal z distribution. Each t distribution is more spread out than the standard normal distribution. For example, here we have our z curve, and here we have a t curve with 2 degrees of freedom. Why is the z curve taller than the t curve for 2 degrees of freedom? Let's take a look at that. Well, as the number of degrees of freedom increases, the spread of the corresponding t distribution decreases. So if this is for 2 degrees of freedom, this would be for 8 degrees of freedom. And we can also say that as the number of degrees of freedom increases, the corresponding sequence of t distributions approaches the standard normal distribution. So if we were to add in a t curve for 5 degrees of freedom, we'll see that that is closer to our z curve than our t curve with 2 degrees of freedom. So for what degree of freedom would the t distribution be approximately the same as a standard normal distribution? Now, once the number of degrees of freedom exceeds 30, critical values change little as the number of degrees of freedom increases. And so usually for degrees of freedom greater than 120, we use the z critical values there. So what about confidence intervals for mu when sigma is unknown? Well, the general formula for a confidence interval for a population mean mu based on a sample size n, when x bar is the sample mean from a random sample, the population distribution is normal, where the sample size n is large, n is greater than or equal to 30, and our sigma, the population standard deviation, is unknown, is going to be x bar plus or minus our t critical value times s divided by the square root of n. So where the t critical value is based on the degrees of freedom of n minus 1. And our t critical values are found in table 3. Now this confidence interval is appropriate for small n only when the population distribution is at least approximately normal. Let's look at an example. So the article "Chimps Aren't Charitable" summarized the results of a research study published in the journal Nature. In this study, chimpanzees learned to use an apparatus that dispersed food when either of 2 ropes was pulled. Now, one of the ropes was pulled, only the chimp controlling the apparatus received food. And when the other rope was pulled, food was dispensed both to the chimp controlling the apparatus and also a chimp in the adjoining cage. The accompanying data represent the number of times out of the 36 trials that each of 7 chimps chose the option that would provide food to both chimps, a charitable response. So we're going to compute a 99% confidence interval for the mean number of charitable responses for the population of all chimps. So first we need to verify that the conditions for a t interval are met. So let's suppose it is reasonable to regard this sample of 7 chimps as representative of the chimp population. Now, since n is small, we need to verify if it is plausible that this sample is from a population that is approximately normal. So we're going to use a normal probability plot here. So we're going to go and plot that. Now notice that the plot is reasonably straight, so it seems plausible that the population distribution number of the number of charitable responses is approximately normal. So that's going to give us an x bar of 21.29 and an s of 1.80. And our degrees of freedom are going to be 6. So we're going to go ahead and we're going to plug those values in. And our t critical value for a 99% confidence interval from our t table is 3.71, which gives us a lower bound of 18.77 and an upper bound of 23.81. So what does that mean in context? Well, it means that we are 99% confident that the mean number of charitable responses for the population of all chimps is between 18.77 and 23.81. What about choosing a sample size? So the bound on error of estimation associated with a 95% confidence interval is capital B equals 1.96 times sigma divided by the square root of n. So doing some algebra, we can solve this for n. which is going to give us 1.96 times sigma divided by capital B, all squared. We can use this to find the necessary sample size for a particular bound on error of estimation. This requires sigma to be known, which is rarely the case. Now, when sigma is unknown, a preliminary study can be performed to estimate sigma, or you can make an educated guess of the value of sigma. And a rough estimate for sigma is used with distributions that are not too skewed, is the range divided by 4. So let's look at an example to kind of see this. So the financial aid office wishes to estimate the mean cost of textbooks per quarter for students at a particular university. For the estimate to be useful, it should be within $20 of the true population mean. So how large a sample should be used to be 95% confident of achieving this level of accuracy? So the financial aid office believes that the amount spent on books varies between, most values between $150 to $550. So to estimate sigma, we're going to take the range and divide it by 4, which is going to give us $100, which is kind of a nice value to use. So we're able to plug that into our equation for n, which gives us 96.04, and we're going to go ahead and round that up. You always round up your sample size up to the next whole number, because you can't have a portion of a sample size. So in this case, we would have a sample size of 97. And that is how you can calculate your sample size.